Okay, it's 9 a.m. here in Germany. Welcome again to our webinar today. I think we are ready to go now. My name is Victoria and I am your host today. Before we start, I will give you a few remarks for your information. Please feel free to type in any questions that come up during the webinar in our question box. You should see it at the top or right side of your Microsoft Teams window. The icon looks like a speech bubble with a question mark. We will answer as many questions as possible at the end of the webinar. If there are too many, don't worry, we will answer each question via email within the next days. If there are any technical problems, please don't worry. This webinar is being recorded for you, so you will automatically receive a recording of the webinar within the next 2 days by email. And one last piece of information, this webinar will take place again today at 5 p.m. German time, which is 11 a.m. Eastern USA time. If you have colleagues for whom this time might be more suitable, please forward the registration link, which I will post to you as a message. Well, now I would like to introduce you to our today's speaker, Dr. Elena Mukina. Elena studied physics and mathematics at the Yaroslav State University and has a PhD in physics. She has been part of the Netsch analyzing and testing family for over 20 years now and has gained lots of experience in our R&D department before taking over the position of the business field manager for the software Kinetics Neo last year. Elena has been a huge contribution to the development of the Kinetics Neo software, which she will demonstrate today. Welcome, Elena. We are happy to have you here today talking about ceramic sintering, kinetics simulation, and process optimization using the Kinetics Neo and Thermica Neo software. I will now hand over to you to get started, so enjoy our webinar and have fun.
Thank you very much, Victoria, for kind introduction. And hello, everybody. I see we have a lot of people here right now, and I'm really very happy about this. And today we would like to speak about ceramic sintering. You know that we are from the company Netsch, and this company is located in Germany, in the city Zelb, which is famous as a city of a production of a porcelain and ceramics. And our company, Netsch, was founded more than 150 years ago. And now, this company, our company, was founded specially for the building of machine for ceramic industry. So this is our specialty. Right now we have 3 groups, 3 business units, and more than 4,600 employees. And it is located around the globe more than in 200 points, and it has 3 business units: analyzing and testing. It's our unit. We produce the instruments for thermal analysis, then pumps and systems, and grinding as dispersing. This is our sister company, and it also produces the machines for the ceramics. And probably it will be interesting for you just to see that this company, Netsch grinding and dispersing machines, produce the dry grinding machines, which is used for the ceramic production in the big volumes, and also Netsch mixing and wet grinding machines. So for those of you who are interested in the big machines, it could be also interesting. And now about our part. We produce the laboratory measurements, laboratory instruments. For example, SCA. It's simultaneous thermal analysis for TG thermogrametry and DSC, differential scanning colorimetry. Then dilatometry, LFR, laser flash analysis, and so on. We use it if the customer would like to know what is the behavior of material at some temperature, which could be measured. For example, for known time, for known temperatures, which are inside of our range, of our measured range of our instruments. But sometimes, especially for ceramic, situations, the temperatures are high, and they are higher than the temperature which we can measure. And in this case, in order to know what happens with material at high temperature, as we can measure, we use a software which called Kinetics Neo software. It works also for milligram and for known temperature. It takes data which are measured in laboratory. After that, we create a kinetic model which is based on this data. And after that, we can use this model in order to simulate what happens with the material outside of our measured range. For example, at the temperature which are higher than our measured range, or what happens during your industrial process, during the production of ceramics. Because of course we cannot put our laboratory instruments during the production process, but we can use Kinetics Neo to simulate and to see what happens. This is our first software package, which works with a small amount of material and works with uniform and known temperature. But sometimes, especially with ceramic production, we speak about a bigger amount of material where we have gram, maybe kilogram. And in this case, there are some temperature gradients inside the volume. And these temperature gradients play a role for the quality of the ceramics. And in this case, the temperature is different at different point, and we must take into account these temperature gradients. For this case, we use our software, which make a simulation in the bigger volume. It's called Thermica Neo software. It works for higher amount of material, and it takes into account temperature gradients, and it can show how a reaction goes on inside the big volume of material, how the sintering, how the debonding goes on. Now we will speak about these two packages, Kinetics Neo and Thermica Neo. Let's start with the first one, Kinetics Neo. If we produce the ceramics, for example, medical ceramics, high-tech ceramics, then the quality must be high. Sometimes if we use the microscope in order to see what is inside ceramics, then we see the cracks. And these cracks shows us how high is the quality of ceramics. And we would like to have the highest quality and to avoid the micro cracks if it's possible. In this case, we must take into account the heating rate during our production. So if everything goes slow, then the quality is higher and then we have less microcracks. If we make the heating very fast, then there are some temperature gradient inside and the shrinkage is not uniform, and therefore there are mechanical stresses and the quality could be decreased. So it should be some kind of optimal temperature program in order to get a best quality in the shortest time. So it must be as good as possible, but as short as possible, because for longest time the quality will be good, but it will be at high temperature very expensive and sometimes is economically not reasonable. In this case, we use our instrument in order to see inside the firing process of ceramics. There are two parts. The first part is below 700 degrees C. Here we have debonding of polymer, and we can measure this process with a thermobalance, with thermogrammetry. The second one is above 700 degrees C. It's densification of our ceramics. Here we have the changing of the length of our material, and we can measure this changing of the length with dilatometer. Here above 700 degrees C we can use dilatometer. How it works? For example, below 700 degrees C we use our SCA measurement. We take our material in laboratory, we make heating and measure the mass loss. At the beginning, we have initial mass, then we have a final mass, depending on the temperature. And somewhere where at some temperature, decomposition happens. But it happens not always at the same temperature. If you make a fast or slow heating, then this decomposition happens either at lower temperature or at higher temperature, because our process is kinetic process and it depends on time and temperature. This was the point, and here, for example, we just make a measurement with 0.1 K per minute, real measurements 1 K per minute, 10 K per minute, and we have 3 different curves depending on the temperature, and we see that here is the first decomposition step and here is the second decomposition step. Then inside our software, Kinetics Neo, we can create one kinetic model. Here is the first step, A goes to C, and then the second step, B goes to C, and then we can create one model, and this one model must be independent on time and temperature. So each contains the parameter which is independent on the time and temperature process. For example, activation energy. For example, the concentration of initial reactant, concentration of the product, concentration of intermediate reactants. It depends on the parameters like pre-exponential factor. So some parameters which are independent on time and temperature, and behind of this model is Arrhenius reaction, Arrhenius equation, which shows how reaction rate depends on these parameters and depends on time. So we can put in this model the value 0.1 K per minute. We can simulate the curve, the decomposition curves for 0.1 K per minute and see what happens. We have as a simulated curve, the red curve, and we can compare it with the original experimental data. We can do the same for another heating rate and of 1 K per minute and for 10 K per minute. And in this case, we can compare the results of this one model with our experimental data. And if this model works well for all experimental data, for all different heating rates, then it means that we can take this model and make a simulation at other temperature and other heating rates. And here again, we take experimental data, we create a model, and after that, we can use this model inside our software to see how decomposition goes on under any temperature program. For example, under temperature program during your production process. Or, for example, here we can take some temperature program with heating and isotherm and see what will be decomposition for this temperature program. And for optimization, for example, here we can think that it's some example. We have some temperature program which contains which has some isothermal and heating segments, and for this temperature program, we have a curve which shows decomposition profile. The second picture is the first derivative of our simulated curve, or just a curve which happens during our production process. And now, if we would like to see how to optimize our production process, our industrial process, we can find firstly points where the reaction rate, the decomposition rate is the highest. So it means that the points where we lose the quality. And we must additionally find the points where reaction rate, decomposition rate is too slow, so where we lose the time. Why we lose a quality here at this point? Because during the very intensive decomposition of polymer, we have production of gas because of decomposition. And if this happens very intensive, then usually for the pressed ceramics, there is no time for this gas to go out from our ceramics. And then this gas can destroy or damage the structure of our ceramics. So we must avoid the points with very intensive gas production, with very intensive decomposition process. And here, for non-optimized process, we have 29 hours and 0.5% per minute. Here is the maximum decomposition rate. After optimization of this process inside our software, we can make a little bit slow here in this range and a little bit fast on the range with a slow decomposition. And here are our result. We have optimized 18 hours, maximum 0.16% per minute. So here the maximum decomposition rate is almost 3 times less. So we have increased we have decreased the decomposition rate, we have improved the qualities, and we have reduced the time during our sintering process. So these are optimization of debinding below 700 degrees C. And now here we have an optimized temperature profile, something like this, and more or less constant decomposition rate. Here is our result. And now let's see what happens above 700 degrees C. We take dilatometer, our dilatometer, we measure the changing of a length of our ceramics. We measure densification process. Here is our result. We have originally the thermal expansion. After that, there is a sintering, so the changing, reducing the length of our material. And after that, we have thermal expansion after the sintering process for the product. Again, we have some temperature points where everything happens. And again, the same like it was during decomposition. Here, a result depends on the heating rate, how fast we make heating during the sintering process. For slow heating, everything happens at lower temperature, and for fast heating, our sintering, our shrinkage happens for higher temperature. And again, we can take our data, real data. Here, the thermal expansion is already removed. We have step number 1, step number 2, step number 3. We have create 3-step reaction. A goes to B, B goes to C, C goes to D. And after that, we can take this data and simulate the densification or just shrinkage during our industrial process. We put our temperature profile during our industrial process into the software, and we can see how the length change, how the length changing during our industrial process. Here, the dashed line is the temperature, and a solid line is the changing of our size. That was original non-optimized temperature profile. For this non-optimized temperature profile, we can calculate a first derivative and see that here somewhere the shrinkage is very fast. Shrinkage rate is very fast. And it means that for very fast shrinkage rate, we have some mechanical stresses. And here we can, the process can provide some cracks in material exactly at this point. And in order to improve the quality of material, we must reduce the heating at this position in order to make this shrinkage rate a little bit slow. And again, here and here, for example, we see that the shrinkage rate is very slow. Again, here it is very slow. And in these points, exactly here, we can make a heating or isotherm a little bit shorter or heating a little bit faster in order to make the process a little bit more intensive and not to lose the time. That was originally at 25 hours, and 1% per minute is the maximum densification rate or shrinkage rate. After our optimization inside our software, we have finally a result 9 hours. It's more than twice less, and the maximum shrinkage rate is 0.4% per minute. So it's more than twice less. In this case, we have improved the quality and we reduce the total time and we reduced the costs of our material, of our production. That was the one of the first our customers where we have apply this optimization, and that was the company Haldenwanger. It is in Germany, in Bavaria. It belongs to Morgan Advanced Material. They produce a new material which called hollow foam alumina. It's really a foam, ceramic foam, and it was very sensitive to debinding process and debinding and sintering process. And after our optimization, we just make a measurement in laboratory, create kinetic model, and then provide the optimized temperature profile for production of this new material. And during our optimization, we have reduced the production time more than 50%. And these results were published on, were presented on Ceramitech and on NATAS conference. So that was the first one. The second one is very intensive. This is about 3D manufacturing, lithography-based ceramic 3D manufacturing from the our partner, the company Litots from Austria. And here, again, results are present on the conference, Thermal Conductivity Conference 2021. Here, the process of 3D manufacturing use the polymer, which is originally liquid polymer, but it is cured under the light. So it is photocurable material, and it is during the production we have layer by layer, and each layer is covered with a liquid material, and it is cured. It is cured by the light, and after that, finally, it becomes to be cured and not liquid anymore. And during production, we need decomposition of this material. So during TG data, we have 4 steps here, 1, 2, 3, 4. After that, 4 steps kinetic model was created, and this model will be used for the simulation. For example, here we can see how decomposition of this material happens at different isothermal conditions. For example, for 500 degrees C, it happens immediately during 4 or 5 minutes, and for maybe yellow 200 degrees C, we have decomposition of the first step at the beginning in first 20 minutes, and after that, after 2 hours, we have decomposition only of 10%. That was a second point. That was about the using of our KineticsNeO software for optimization, for creating of a modeling and optimization process. But usually we must know what happens for non-uniform temperature, where we have a bigger amount of material. For example, here, if you go to some porcelain museum and see a big volume of material, then you see some cracks everywhere. And these cracks, they just coming because the production process was too intensive. And then there are some big high temperature gradients inside the volume, and then there are some mechanical stresses which provide these cracks. During our production, we must avoid this. We must avoid these cracks, and therefore we must know exactly what are the temperature gradient inside our volume. So in this case, we can just use our second software, which is called Thermica software. Here we can work with non-uniform temperature, and we can calculate how the process goes on in the big volume. And we can speak here about both processes, about debonding and about sintering. How it works. We can take internally a small amount, a small volume, a small amount of material. We can calculate how many energy comes in, how many energy goes out. We can calculate how many energy is produced because of chemical reaction. For example, sometimes it is important during decomposition. Then we calculate a heat balance, and then we can see how if this heat balance is positive or negative, and if this small amount, small volume, make self-heating or self-cooling. And after a couple of mathematics, we have a normal heat transfer equation. So inside our software, we solve this heat transfer equation together with the chemical equations corresponds to our kinetic model. And kinetic model is taken from the first software package from the Kinetics Neo software. So the data for simulation, the first data for simulation is our kinetic model. We just take it directly from our software. There is no is not necessary to transfer each parameter and each equation from one software to another. You just select your kinetic project, and then you have a result here. Here, for example, we have dilatometer measurements for silicon nitride, and we have a 4-step model for it. That was a first data for simulation. Additionally, for simulation, we need the physical data. And these are specific heat capacity, density, and thermal conductivity. All data must be temperature dependent because they have the high difference between the values at room temperature and the values at high temperature during our production process. For these physical properties of the mostly used materials are inside our material library, and you can just select, for example, material, this silicon nitride green body here in our material library, and then specific heat density and thermal conductivity are already inside your project. This is the second point. Sometimes, especially for ceramics, the physical properties of material are not the same for original green body and for ceramics after sintering. Here we have the green body before sintering properties and after sintering. Specific heat is more or less the same, so it is it is increasing, and final value is about 1. It's okay. But for example, with density, it is totally different. You know that during the sintering of ceramic, we have this densification. And finally, the density of our product, of our ceramic product, is much higher than the density of original green body. So, for example, here for silicon nitride, original green body has the density about 1.7, and after the sintering it is more than 3. So it is almost factor 2 the changing of a density during our process. And the next one is thermal conductivity. And here the changing of thermal conductivity is really very high, because at the beginning we have a green body as a porous material or just a mixture with the polymer. And after that, after all sintering, we have material which is almost solid with the crystals inside, and the thermal conductivity or crystals or glasses inside, and then the thermal conductivity of a final product is really much higher than the thermal conductivity of original product. For example, here for silicon nitride, thermal conductivity of original material before sintering at room temperature is 0.5, and for final temperature, for final product after the sintering, it is 13 watt per meter Kelvin. So it is almost factor 25. It is a really very, very big difference between the thermal conductivity. In this case, we must take into account the changing of our thermal conductivity during the sintering process. So it means that during the simulation, we must not only see how thermal conductivity depends on the temperature, but we must calculate the concentration of initial material, concentration of final material, and calculate the intermediate value of thermal conductivity and use it and see how it works. Otherwise, the results of simulation will be not correct. That was the next point. And of course, we must select the geometry, and for geometry it could be a different properties on the top, on the bottom, on the side. We can select the emissivity coefficient. For example, it depends on the color of material. For the black ceramics, it will be totally different as for the white or yellow ceramics. And all this data of emissivity, they are already in our material library. You must not take it, search it somewhere. You can just take it from the material library. If it's necessary, then you can just use some substrate on the bottom of your ceramic pot, or if it is necessary, you can just use some material on the top and on the side if it's necessary. If not necessary, then you can skip it. And now results could be shown. For example, for the cylinder, you can select at different points on the axis and see the temperature on each point on the axis, on the vertical in axial view, for example, for the rotational body for cylinder. Or another one, you can just make the radial points here and compare the temperature at different radial differences. And here you can select different vertical positions. So you can put this radial points close to the top or close to the bottom. This is the results, and as a result, you can see the temperature like it shows here. You can see conversion rate, or concentration versus time. Here we have different thermal conductivity before and after reaction. I already told you that 0.5 is thermal conductivity of material before sintering, and 13 is the thermal conductivity of the product. Inside the software, you can select the material before sintering with its physical properties, and material after sintering with another properties. And then during the sintering, the software is calculated at which time and at which temperature the sintering happens, the shrinkage happens. And exactly at these times, the software recalculates a value of thermal conductivity. You see that before the before sintering, we have a lower value of thermal conductivity, and we have a big difference between the temperatures at different points inside our pot, because thermal conductivity is not very good. And after that, after sintering, somewhere here, for example, we have a less difference between temperatures at different points of our pot. Why? Because the thermal conductivity is higher, and here we have a changing of our thermal conductivity, and it is taken into account, of course. And the next part shows how the density, the changing of a density is shown inside the software. So here we have for green body a density before sintering is 1.7. After sintering for the product, we have a density 3.1. And our software, Thermica software, will show you the real size of your material. For example, for the green body, it will be a big size, and for the sintered material, it shows only a small size. It is presented in the software. And how it looks like, for example, here for the cylinder, we show that the size of material will be decreased. And for the vertical section, we see that it is also decreased. We can also see the concentration of each component during sintering. For example, we have some kinetic process, and this kinetic process has the steps A goes to B, B goes to C, and then C goes to D and to E. In this case, B, C are the intermediate components. You know that during the sintering process, sometimes some crystallization happens, some recrystallization happens, and we can speak about some intermediate material or intermediate components. And in this case, inside the software, it is possible for each time points, like here, for example, 55 minutes, we can see the concentration of each component. Concentration of A here, concentration of B, C, D, E, and so on. We can also see the concentration of this reactant as a function of time. Here is the concentration of A, B, C, and D, and so on. So here it is possible for you just to see inside your process and to simulate what happens during your process, or maybe during your production process. Now we can create in our software not totally arbitrary geometry, but we can use, for example, we can apply, for example, rotational geometry with arbitrary profile. So it is two-dimensional arbitrary like this one. And here we can calculate a temperature conversion rate. You see how it looks like here during the simulation, and we can make some temperature profile here or temperature profile here. Now I have a few minutes just to show how it looks like inside our software. So the firstly is our Kinetics Neo software. Here we have alumina. We have the sintering of alumina, and the measurements are dilatometer measurements with 3, 10, and 30 K per minute. And here I just, we can create either TG or dilatometer data. I just loaded this data. After that, we can open analysis and create a kinetic model. For example, now I just create with one click the model-free kinetic model. Here we see the points are experimental data and the lines are our simulation according to this model. And we see that this one model can describe all three curves, which are measured at different experimental data. And now we can take this model and make a simulation for some temperature profile. For example, here is a multiple step. I can just see this as a temperature or time and see that here dashed line is the loaded temperature profile, which is still not optimized, and the solid line is the changing of a length, which is calculated with the software using our kinetic model, which is created right now. And if we calculate the first derivative, then we see how it looks like. At 5 hours, it is the highest. Now we must reduce here the heating rate. For example, here we just put 0.2 K per minute. And now you see the peak is not too high as it was. And for some points, we can make it shorter. For example, at the beginning, from 0 to 4 hours happens nothing. So it means that the first heating segment must be faster. I just put here higher heating rate. Now it is the first segment becomes to be shorter, and we have shorter the total program. We can, for example, here between 5 and 8 hours, we have the isothermal segment 4 hours. We can make it shorter, for example, 30 minutes. Here, this one, and see, calculate. Now it is short. Then we can make the shorter, the next one, also 30 minutes. Yeah, something like this. Remove the last one. And in this case, we make some optimization. We can make some faster heating between 2 and 4 hours, something like here, for example, I think, or just at the end here, 1.5. Calculate. So here is fast, and here we can make 0.5 per minute. Okay. So this is our more or less, it is becomes to be shorter, and the maximum becomes to be lower. So we improved the quality and we reduce the time. And now is our signal. Signal is more or less has more or less constant rate. So the length change is more or less constant. If it will be faster, then we have cracks, we have some mechanical stresses and cracks, and if it's slower, then we just lose the time and increase the cost. So this is some kind of optimal results. That was for kinetics now, and you can put here any temperatures what you want. You just see many steps. Each step has initial temperature, final temperature, heating rate. You can add a new step. You can remove each step. So you can just put your temperature, or you can just import the data which are recorded as a temperature from your industrial process, and then you can directly see what happens. That was kinetics now. And now about our Thermicaneo software. Here, I just close everything. Here we can create a new project which is empty, or a new project with a library, material library. Here I just take a first data for silicon nitride. We can just see it as a function of temperature or as a time. The kinetic data just normally are taken from our kinetic project. So it is not necessary to put each activation energy or reaction order or each reaction step from one project to another. They are totally compatible with each other. You just open Kinetic Project and everything is here. After that, for this material, it is necessary to select the physical properties. Here we say that there is a different properties, physical properties for original material and for final material after sintering. We select silicon nitride green body from the library for initial material and silicon nitride sinterate again from the library for the final properties. And here, for example, for initial material, we can see specific heat density, thermal conductivity as a function of temperature. And in material library, we can just say for sinterate, for example, this is the specific heat density and thermal conductivity, which will be used during our simulation. Now I go back. That was a material. Now we select geometry. We can just select a geometry, for example, cylinder, or it could be something like slab. Yes, it is changed. We can create some substrate here and select material for each. And for the first one, we can remove substrate, so it's up to you, or we can remove for all of them here, or we can create another shape, for example, arbitrary shape. And for each surface, we can set if there is some substrate or some container material. It's called, so as we call it inside our software, or we can switch on the radiation, because for high temperatures, the radiation, the emissivity is very important process for the heat transfer on the surface. That was the second point. What is also should be selected here for the surrounding. For the surrounding, it is important the heat transfer between our surface of our ceramic and the surrounding. And for ceramics, it is usually air, but this air can have a different flow rate. And of course, if the flow rate is low, then the heat transfer will be not so high as for the situation if the flow rate is high, flow rate of the air. And in this case, we have in the library a different, the air, which has a different flow rates, and you can select your case, which corresponds to your oven, to your furnace. And after that, you will have the correct heat transfer between the surface of ceramic and the surrounding. Here it is selected, and after that we can select a simulation. For example, for this one, we can put again a temperature profile of the surrounding temperature of the air. For example, it could be, this air could be measured in your furnace, and after that we can make a simulation and see how it looks like. For the simulation, there is a possibility to make a roughly simulation, and it is fast. It is selected right now, or we can select the fine simulation, and it will be very, very slow. For our body, for our part, we can select either radial results or axial results. You see here on the top plane, we can use either vertical plane or horizontal plane. And for a radial plane, we can just see if the results are close to the top or if the results are close to the bottom. Here we have the temperature. We can see also conversion or maybe conversion rate, something like this. That was 2D graphs depending on the time. Or we can select a section as the heat map I will select the radial and see how the temperature changed. So this is a rotation body, and we can see how the temperature changing during our simulation. This is our result. We can see also the conversion. It's a shrinkage, degree of shrinkage, how it goes on inside our simulation. You see, and you see that the changing, you can see the changing of a linear size of our material. And we can see also the concentration, a concentration for A, concentration for B, for A, for B, for C, for D, so for E. So these are our results. And now let's go to the final slides of our presentation. Thermica can calculate temperature, degree of conversion, conversion rate, concentrations. Our kinetics is based on the current state of ICTAC Kinetic Committee recommendation for analysis of multi-step kinetics. And we correspond, we are inside this project, and we fulfill all these recommendations. And inside our software, so we have a website for KineticsNair and for ThermicaNair. You can just go on kineticsnair.com or thermica.com and get a trial version for 30 days. Inside the website, you can say request trial version, and after installation you can go to the learn section and just to see some training examples which are done specially for centering. That's all from my side. You can write emails, and now your questions.
Thank you, Elena, for this great presentation. We are now online to answer a few of your questions, so please feel free to let us know all of your questions in the Q&A area. As I already said, it should look like a little speech bubble with a question mark. This is where you can type in your questions. Elena, whenever you are ready, I would start because we have already a few open questions. I would read out loud the first one. The first question is, I would like to ask how you know what type of reaction model you should choose for each reaction. Do you know it from literature, or do you try many models and choose the one with the best fit according to KineticsNeo? Elena, maybe you can help here.
Firstly, there are some rules which kind of model should be selected. Some of them are written in this article. What kind of model should be selected? For example, if we speak about debonding, then we speak about decomposition process, and then it is usually, each step is usually Nth order reaction. If we speak about densification, about dilatometer measurement or changing of the length, then we have some recrystallization processes internally, and according to the literature, they could be described by the Avrami reaction type. So this is some literature data which are known what kind of reaction must be used for especially for each process. So this is the first part. And the second part, if we don't know, for example, if this Avrami of the first, of the second order, or if this Avrami of the third order, then we can just put it as a free parameter, Avrami of nth order, and then see what is the best one.
Okay, thank you so much for your answer. The next question, what's the maximum temperature net stillathometers can run at? Do you know the answer by heart, Elena?
It depends on the time. It depends on the dilatometer, because we have really different dilatometers. And I know that the highest temperature really highest temperature is 2800, but it is some special type of dilatometer with the graphite furnace, and standard is about 17 standard STA. STA until 700 dilatometer. It depends on the configuration. You can just go to our website and see the result.
Great. Yeah, I think that's a good tip. Then I would go on with the next question. Somebody says the optimization being shown is quite a manual process. For example, tweaking the heating rates and time points manually. Is there any way to use an algorithm or machine learning to optimize the profile further more easily?
Yes, so this is I show you a manual process because for some our customers there are some limitation for the furnace. For example, the furnace cannot go higher than 30 degree K per minute or something like this. So, and therefore we must take into account the limitation of the furnace. But here, do you see my software? And here we have conversion rate, maximum conversion rate is 0.4. We can make the ideal case with 0.4. I just go to conversion rate, here optimization, and I can put here 0.4% per minute, calculate, and this is the result. This is the ideal case, which is not manual. So, and after that, you must try to get your furnace to this ideal temperature profile with the constant conversion rate, constant length change rate for our process. Okay.
Okay, thank you so much, Elena. I would go on with the next question. If we are using non-library materials, is there a guide to creating new library entries? For example, what data is needed?
Yes, it is inside. So here we have reactant. We can add a new material. And after that, there is specific heat density and thermal conductivity, and it is empty. And you can just put the new points. For example, for room temperature, it will be, I don't know, 0.8. And for 100, for 1600, it will be 1.3. And then we see this result. So you can just put, or you can just make the import of data if you have this already as a table. So this is specific heat density, thermal conductivity, and it is everything is written in our in our documentation. So if you have a software, then you have everything.
Great, thank you so much. Thank you, Elena, for the great presentation, and to all attendees, thank you for your presence in our webinar. As I said, and also as Elena said, we will come back to you as soon as possible with our answers. So hopefully we will see each other soon in another webinar, and yeah, enjoy the rest of your day. Bye-bye.
Bye. Thank you. Bye.